to use it, and how do you formulate the problem and how to start using it. So like I said, first we need to do some kind of feasibility study where you assure yourself that you really need a neural network for this. It's not a simple problem which you can represent by some matrix transformation or linear transformation, something like that. So then you need to identify the inputs, exact outputs, and more importantly, this is sometimes neglected. You need to have enough domain knowledge to be able to formulate an optimal neural network solution to the problem, right? And so, what is this domain knowledge? So you need to know enough about the domain where you are trying to formulate a neural network problem, because so although the approximation theorem ensures or guarantees that the neural network can learn any mapping practically from any x to any y practically on a finite domain. You cannot just use it like a in a brute force fashion. You should understand the problem well, and you should also be able to have an insight uh, which will help you break up the problem into convenient modules. Right? You can't just take the whole thing and just train it on a big neural network. So then, when you break up the problem into smaller problems and then map each of the smaller problems onto separate neural networks, then figure out how to collect data for each of the modules and how to do the data processing and things like that. So we look at an example of this kind of mapping of a big problem onto neural network in the next class, where we look at the problem of protein structure classification, secondary structure of proteins. So proteins have this alpha, beta, beta sheets, alpha helices, and all that, right? So given a local sequence, the amino acid sequence of the protein, how do you classify this local structure? So for that, you can just take one big network and classify it and formulate the problem, or you can try to break up the problem into multiple problems and train individual networks and then combine their decisions using another neural network. So all those decisions, to be able to make those decisions intelligently, you need to understand something about the problem. So one more example is where I'm familiar with is the problem of OCR, that is optical character recognition. Let us say you have the problem, you have a document, and you scan it and you get an image, and you want to identify the characters in the image and reconstruct the document. Now, since the approximation theorem guarantees that you can learn any mapping, right? You cannot just take whole pages and train neural network on that. That will be very inefficient. You need very large number of pages. Whereas it will be more efficient if you could first segment the document into separate regions like paragraphs and images and things like that. Then take each paragraph and segment them further into lines and words and ultimately to characters. So which is itself a very hard problem. And then present each character to a neural network and then make the network classify the character. So to be able to segment the problem like that, you need to understand the problem. You need to have sufficient domain knowledge. Okay, so you cannot ignore domain knowledge. So second thing is data. You need to create a good representative data set, an adequate data set, to be able to create an efficient neural network implementation. Because a neural network is basically, as it is shown in this picture, a kind of an active form of data. Data is passive. In data, you just have a bunch of xis and dis, the input data and the corresponding desired outputs. Okay, so this is in a passive form. A neural network basically is an active form of that because it takes the same input x and computes y, right, which is like d. So this makes the data and takes the data and which is in a passive form, converts in an active form. So the neural network is only as good as the data. So you need to make sure that the data is good enough, and so for which again you need domain knowledge. So what is a good data? It should be abundant, and so very often you may not have enough amount of real data. Sometimes you do, sometimes you have too much of it, but sometimes you don't. So then you need to have take real data, and sometimes you have simulators of the process that you are trying to understand. And so use simulated data and augment the real data with simulated data. right? And then use that as a data set. And then it must be comprehensive. It must include all possible cases. So, for example, suppose you are doing again protein classification. You have this alpha helices and beta sheets, right? And so, if you have only alpha helices in the data, right, and no beta sheets, and you will never be able to classify beta sheets. So, you need to make sure that data includes all possible cases. It should be reliable. You need to make sure there are no errors, no bugs in the data. And another thing is right representation is the key. What is representation? Let me give an example. So let us say I take this problem of odd even discrimination. It's a very silly problem, but it gives an insight into how the correct representation can make a difference. So suppose my problem is I give a number, right, to a neural network, and it should classify it into odd or even. It's a very simple problem. So when I give a number to a neural network, obviously you have to convert it into a vector. Now let us say I take only numbers from 1 to 100 to just keep it simple. So it's only two digit numbers. So how do you represent two digits? So I have like something like 45. So how do you represent this as a vector? And usually the vectors that we use in neural networks are binary vectors. Okay, it doesn't have to, but usually it's binary vectors. So one way to convert a single digit into binary vector is like have 10 slots. So 4 would be 0, 0, 0, 0, 1, 0, 0, 0, 0. So that is, this stands for 0, this stands for 1, this stands for 2, and this stands for 3, this stands for 4. And so like that you can represent a single digit as a binary vector of 10 dimensions. Okay, similarly another 10 dimensions for 5. Let us say this 20 dimensional binary vector can represent 2 digits. So now you train this network on this 20 dimensional binary vectors and you can classify it into odd or even. You can do it, it's not impossible. But it's a fairly hard problem if you pose it like that. Because odd or even depends only on the last digit. And not only that, imagine that you represent this in binary form instead of decimal system. So this is decimal. Suppose you do this in binary form, right? Okay, you have some 0, 1, 1, so something, something. Okay. So now whether it's odd or even simply depends on the last bit, right? If the last bit is 1, okay, it is odd. The last bit is 0, it is even. As I don't even have to see any of the other bits. So the problem becomes trivial. So what was so difficult when you represent the number in decimal system, and then some kind of binary which is derived from decimal system becomes quite trivial when you present in binary system. And this kind of it's like a hack. This hack is good only for this problem. But some other problem this won't work, or even it might even become too difficult. So this is an example of how your insight into the problem can give you better formulations of the neural network solution. So you should also this has got to be the representation of data. Then you should also try to remove irrelevant or redundant information. Irrelevant because if you have input dimension, input vector which has lots of features, lots of properties of some process, and if you know from your understanding of underlying physics that some of the parameters which were taken are actually relevant to the output, then that analysis will help you remove those kinds of variables. Similarly, you'd also do normalization. You need to make sure that all the numbers are about in the same range. Otherwise, you'll get bad fits, right? And scaling, normalization, all these things you do to clean up the data. Then the input dimension should be as far as possible small, because if the input dimension is high, the requirement of the data increases exponentially with the input dimension. I think I once mentioned here. So the input dimension is just one dimension. So my input, okay, so n is equal to 1. And I want to have a resolution of like 10. So my resolution is d equal to 10. So I just need 10 data points. But if the same resolution on each dimension, input dimension is 2, right, then I'll have, okay, so I need to have so d square data points. Okay, so similarly as input dimension increases, I'll require d power n data points. So my requirement on the data points, so my training set size increases exponentially with the input dimension. So people take a lot of care to reduce the input dimension by some kind of a transformation. So one of them is principal component analysis. Other is feature extraction. We'll talk about this PCA later, maybe in the next week, one of the classes next week. So once you have the data all sorted out, the next thing is architecture. So what kind of architecture will you take? And the architecture question is quite simple if you just confine yourself to MLP. But if you come to deep networks and more recent technologies, things get more complicated. Because you have more freedom, you can play around with much bigger architectures. And a lot of variety of architectures are available in the in the contemporary AI. So I may not discuss all that, but I'll discuss some of the deep networks in the next week. So then you have to initialize the network randomly. Typically, the weights are randomly initialized. Then you have train it and then prune it, and then you start using it. So architecture means in a traditional MLP, you just have majorly two questions: how many hidden layers and how many neurons in each hidden layer. So thing is, for both these questions, you don't have a clear-cut answer. That is, given a problem, given a data set, there's no algorithm that will let you just compute the ideal number of hidden layers or ideal number of hidden neurons. And even if somebody promises some kind of nice formula, right, for answering these questions, don't believe it because there is no such formula, right? And even if there's some formula, they are useless because it depends on, often these estimates are dependent on some knowledge of the underlying function which you don't have. Okay, so in practice, the only thing that the option available is to try out different network sizes on a given data set and find out which is optimal. So same thing. So thing is, the approximation theorem, universal approximation theorem, guarantees that a single hidden layer is good enough, and as long as there are enough number of hidden neurons in that layer. But in practice, you may want to sometimes use more hidden layers. So it depends, and always I think you could start conservatively. Start with a small network, one hidden layer, and see if it doesn't work well, then increase, right? And so the advantage of multiple hidden layers, which is what we'll really capitalize when you go to deep networks, is that you can get a hierarchical representation. So we'll see later on in the next week's classes, is if I have many hidden layers, and suppose training this network on face recognition. So my input is some kind of a face, right? And so then if you train network like this, what will happen is typically the lower layer neurons will only respond to some simple, lines and things like that. Because any face or any picture, for example, have lots of short line segments because if you look at the outlines. Then if you go to slightly higher levels, will have neurons which respond to eyes and nose and things like that. If you go to even higher level, you'll find neurons which respond to face types. Okay, male faces, female faces, or bearded faces, and so on. You'll find neurons that respond to those kinds of face subclasses. So you'll have a very intelligent and natural organization, right, emerging automatically when you train a network with multiple hidden layers. Also, it's constrained appropriately for image pattern recognition. We'll talk about that later. So all these things you won't have if you train using a single hidden layer because everything is somehow kind of packed in the same layer in a complicated fashion. So because it has kind of a hierarchical organization when you have multiple hidden layers, it is ideal for transfer learning. What that means is if I have knowledge emerging from one network, and if I want to make use of it to train another network on a different phase data set, then I can just maybe chop off the lower layers right, as it is and move them to the new network and start the new network with these pre-trained segments of another network. Just slap on a couple of fresh layers at the top and train this. This will train much faster because all the lower layers are already pre-trained. Or even if you train the whole thing, because the lower layers already have some knowledge which is relevant to the problem, it will train much faster. So this is one kind of transfer learning, and this will work well if you have a multiple hidden layers and there's some kind of hierarchy in the representation. Okay, so then training, right? You use backprop, and the backprop by itself is a bit slow. So a lot of variations of the algorithm which are faster. For example, you can have adaptive learning, right? You have momentum and all sorts of things. There are also higher order methods where you use higher derivatives, because in backprop you only use del of e, first derivative of the output error with respect to the weights, right? Whereas in higher order methods you also use del square of e with respect to the weights, and this is faster. It is can be computationally intensive, but on the whole, sometimes it can be faster. Now, when to stop training? Basically, when the error goes down, goes less than some threshold value, you can stop training. But you also typically incorporate what is called pruning. Sometimes pruning is done as the training goes on, or sometimes it is done after training is over. So pruning means removing connections which are not very relevant or which are not very effective. They're not really contributing to the solution. So sometimes even if you remove some connections, there won't be much change in the output. Because of all these nonlinearities, certain connection may not even be visible at the output layer. So there are ways of identifying such connections and removing them. So one of them is simple weight decay, and where you just so you have delta W, you just have something like plus my gradient term, that is eta and all that stuff. So the delta W, make sure that the weights are kept as low as possible. Okay, this delta W is equal to minus W term. This is the decay term. So the idea is you come up with a solution using weights which are as small as possible. Okay, so that's an additional constraint. So that is one of the ways of pruning. The other ways were actually identify weights which are not very significant and then delete them. One such this the expression is a bit funny. Optimal brain damage, right? How do you damage network optimally so that you can junk weights, you can dump weights and get the same performance. Then finally, so you can train the network, but how do you make sure that it generalizes well to a new data set? Because it's actually not very hard. Even if you take some junk data, if you just take a big enough network, you can train it to death, and you can get some small error. But point is that doesn't make any sense as long as the network doesn't perform well on a different data set, which is it hasn't seen during training. So that problem is called generalization. So let us depict, try to understand why this problem is important using some kind of a Venn diagram. So basically, what you're doing here is, when you train neural network, is this. So this box, right, represents this is called a set U, which represents all possible functions. So a function is basically a mapping from X to Y. Let us say there is a universe of all possible XY pairs. In that universe, a subset of these mappings, XY pairs, represents some function which you are trying to learn using a neural network. So that subset, let us call it F, which is this outer epsilon, also ellipse kind of a shape, oval kind of a shape. Now, so obviously you don't know that function, and that's why you are trying to train a neural network. So what you do is you take some sample data from that function and train the neural network. Okay, so and the hope is that using the sample data, the network can generalize. So I'm only telling the network about this subset of data. This is the training data at T. So by looking at T, the network should be able to guess that the underlying function is actually this oval, which is F. And that's not easy, right? So how do you test that? Because you don't have access to F, you only have access to some subsets of F in the form of some data sets. So X is another data set which is independent of T, but we know that it comes from the same function, underlying function F. So you need to make sure that the network does well both on T and X. Then you are kind of reasonably sure that it is caught the underlying function. But imagine what will happen if the network has learned something like this. Okay, so this is what network has learned, all right, which completely includes the training data set. So it is done fantastically well on the training data set, but it is generalizing to new parts of this universe of input output pairs, and it is generalizing partly into F, but it's also moving out of F and learning all sorts of irrelevant kind of XY pairs, right? And this kind of a network, if you apply this to the test set X, it'll do very badly. It'll do badly on all of them. Okay, so this can in principle happen, and this is a problem of generalization. How do you make sure that you generalize well to a test set? That's why what you do is you do cross validation. If you have a big, so for that you need to have very large data set so that you have enough amount of data for training and enough for testing. Or if there is a kind of a scarcity of data, then what you do is you divide data set into small chunks, right? And then so take all these chunks for training and use this for testing. And now, so first time you take chunks from 1 to n minus 1 for training, then the nth chunk for testing. Then you rotate it. Then you take maybe use first one for testing and use the remaining ones for training and so on and so forth. Okay, so take look at the average performance. So if the average performance is consistent, and main thing that will tell you that the network is able to generalize well to test set is the training and test performance should be similar. So if you have overtrained the network, what will happen is the training performance will be very good, but the test performance is bad. And that kind of network is not trained well, so it won't. It's not generalizing well. So let me give an example with a simple regression problem. So let us say I need to learn this function. A simple, let's say it's like a parabola, and so I take some data from it, and data points are like this. So there is some noise in the data. So I just have these 4 points. I need to understand that these 4 points come from some underlying parabola type shape. So I train the network, and I train network a very large network, and network has learned this data very well. So it has learned something like this. So let me. Okay, so you see that it's going through the network fit is going through all data points, and it's done an excellent job, right? But look at this; it has completely missed the underlying parabola. So now if you give new data points, so somewhere I want to find out the value here and here, whatever here, all right? And so the network predictions will be so off, all right? It'll be huge error, from the. So this is a network prediction where this is actual function output, right? So it is done very badly. It's missed the function, but it's done greatly on the training data set. So this is a situation which is called overtraining. Why is it happening? Because the underlying function is very simple. It's just something like y equal to x into 1 minus x, something like that. So just a quadratic function. So whereas we must have used like very large number of hidden neurons. So that's when you get such a very complicated wiggly kind of a fit. So whereas a smaller network will give you a fit which might look something like this. Okay, so maybe something like this. This is quite likely if you use smaller network. So what does that mean? So the problem complexity must be matched by the neural network complexity. So that's why throwing a big network, just because you have the program, the memory in the computer and all that, just throwing a big network is not a good idea because you get best fit to the underlying function only when the network complexity is roughly the same as the problem complexity. So this is where you have to do trial and error and make sure that the performance is good not only on training set but both on training set and a separate validation set. So this is where you need. So even if you take a large network, right, the complexity of the network depends on number of free parameters. which is weights, thresholds, everything. Okay, so which is why even if you have a big network, when you do pruning, right, you throw away weights which are unnecessary. So that way you come up with a network which is of more optimal complexity compared to the problem. So this is very important to come up with a network which has good generalization. So let us look at a couple of applications just to get a feel for how you formulate a neural network application. In next class, we look at some applications in biology. So these are the applications. The first one is what is called, this class I'm just looking at some artificial applications. So next class we look at more biology applications. This first one is called a glove talk. So in this application, the person wears a glove, an electronic glove, and makes some gestures, and those gestures are converted into speech sound, and which is given to a speech synthesizer. So the synthesizer will then speak. So basically, your hand movements are converted into speech sounds, right? So it's like a glove talking. So that's called glove talk. So for this, they use electronic glove called the VPL data glove. It has two sensors on each finger, so which measure the finger flex angles, the angles of the finger joints. Then another sensor at the back of the hand, which measures the position. So there's some kind of a accelerometer which is integrated to find position, and also the three rotations: pitch, yaw, and roll. So totally you have 16 parameters. So two on each finger, and for the joint angles, then three positions and three. So 5 times 2 plus 6, 16 parameters. The sampling rate is 60 hertz. So this is the rate at which you are getting this information from the hand, from this glove. So from this, you need to produce speech sounds, and so this is obviously English is the language for this in this case. So so this information goes to a preprocessor, and then first it is fed into one main network, which is called hand trajectory strobe time network. And then this is used to segment your hand, because when gesturing is done continuously through time, whereas the speech that comes out is in the form of words. So you need to segment your your gestures into separate words, and that is done by this strobe time network. So then this is passed, information is passed in separate networks, because the word that is represented in this problem is broken up into two parts: the root word and the wording. Okay, so you need to process them separately. So let me look at these features in this network. So for this problem, they just take a very small vocabulary and create gestures which only represent those small set of words. So for example, this is come, this is go, this is I, this is you, and so on. So this hand gesture or hand shape codes for the root word, and then they use some separate representation for certain word endings. So normal means there's no separate ending, right? And that is indicated by the direction of motion. So here the hand shape represents the root of the word, right? And whereas the hand motion direction represents the ending. So if the hand moves downward, that's a normal case where there's no separate ending. If it is S ending, then move it upwards. If it's ED ending, move towards the user, towards yourself. If it's ING ending, like present continuous tense, move away from the user. And ER ending to the user's right, and LY ending, like in adjective, right? Quick and quickly, right? To the user's left, and so on. So there are some kind of a conventions to indicate the word ending. So like that, they have taken 66 root words and 203, totally 200, with a lot of endings to produce 203 words, and network is trained well. So actually, sorry, uh, I'll get a video of, which will demonstrate this system. There are much more, later versions of the system which are very sophisticated. In fact, the presenter, right, has practiced, presenting certain poetry using the system, and it's really good and it sounds very natural, but for a few sounds. And this guy also recites Dr. Seuss's poems. So I'll maybe try to show that video in the next class. So then another network which was at that time it was not very popular, but that this is one of the networks, one of the models which has led to the deep network revolution in the middle of first decade, like in the 2000s. This is called the convolutional neural network, which was first developed in the late 90s. But at that time, it didn't really get much attention. So this network was developed as actually a variation of MLP. It's a special case of MLP. Uh, and this was developed to read zip codes or pin codes on US postal envelopes. So these are handwritten numbers, so which are very hard to read. So they developed this system so that you can read the pin code and then automatically create a barcode, which is then just pasted on the envelope so that it can be machine read later on. It was giving 99% accuracy at a rejection rate of 12%. That is, if the network doesn't know what it is looking at, it will say pass, and then that is given to a human reader. At that level, it was giving 99% accuracy. But the more recent convolutional network solutions for this problem of digit recognition, there's something called MNIST database. It's really cracked it. I mean, it gives you something like 99.5, 99.6%, and so on. It's really good. But this is a very old system. So how does it work? The input is presented as an image. The input is an image. This is actually a major departure from traditional MLP applications. Because traditionally, if you want to apply MLP and if you want to solve a image pattern recognition problem, you take the image and extract some features, what is the height, what is the width, and all sorts of number of occurrences of T junction, number of occurrences of X intersections, the number of occurrences of loops, all sorts of things. So people generally do lots of pre-processing and compute these features, create a feature vector, and then that's what they present to the MLP. That's what they would do it in the earlier days. But with the convolutional network, they have figured out a way of presenting the raw image as it is, without doing any hand holding and all this massaging. So present the image as it is, and the hidden layers of this network are not single rows of neurons, but these layers themselves are 2D arrays of neurons. Okay, and a given neuron in the given hidden layer takes inputs from a window of neurons in the previous hidden layer. I'll spend more time on all this in the next week when we discuss deep networks, because this is a deep network, because this has lots of hidden layers and so on. So as you go to higher hidden layers, the size of these individual sublayers keeps going down, because here the input image is 28 by 28. Okay, and each of sublayers in the first hidden layer are of size 24 by 24, and next one it is 12 by 12, and so on and so forth. Okay, so the individual sublayers keep shrinking, but the number of sublayers keeps expanding. Right, and the final layer is just 10 neurons, represent the 10 classes, 10 digit classes from 0 to 9. So this can be trained using the same MLP, because it is actually a special case of MLP, because if you think about it, you can unwrap each of these arrays of neurons into one long one-dimensional array of neurons, and then you can connect this, you can take the connectivity, and only thing is, if you just have two one-dimensional arrays in MLP, every neuron in the previous layer connects to every neuron in the next layer. So it's what's called a fully connected layer. Whereas in a convolutional neural network with this kind of a complicated connectivity pattern, you don't have all possible connections. A lot of connections are just zero; they're missing. Right. So therefore, it's a special case of MLP. Therefore, you can use the same backprop algorithm. So when they trained this network on the digit data, they were really surprised. This was done by Lacoon and his team, and they were really surprised because it was able to generalize brilliantly. Right. So initially they trained the network on standard handwritten numerals, and so you can look at this website. What is given in the bottom of the slide, and there is a link in the website to what is called weirdos. So what that means is they created weird kind of input patterns just to test the network, see how much it can generalize, how much it can understand what's going on. So they created a 2 like this and a 4 like this and 6 like this and so on. So in spite of all this weird shapes of these input digits, network is able to classify them and get them right. So look at more such examples. Okay, so in this case, it is even the numbers are constantly stretched and moved around and all that. In spite of all that, it's able to get the output. So we'll see more of this in the next class. So then next example is what is called net talk. So this is a network which can read text aloud. In the previous example, the glove talk, it was converting gestures to speech. Here it's converting text to speech. A very old study from 1986. But you can do a lot better now. You can really get very natural sounding text to speech systems. There are lots of such systems available even in Indian languages these days. So this is obviously done. It's a very old system done for English, and English text to speech is a bit actually much harder than for Indian languages because in English there's no simple mapping between there's no unique mapping between the character and the sound. Whereas that's not the case in Indian languages. In Indian languages, what you see is what you read. A given character is pretty much pronounced in the same way, irrespective of its context. Whereas that's not the case in English because, so for example, C is pronounced as k in cat and sa in facade, right? So similarly, the AVE, um, the single letter doesn't have a unique pronunciation. It's always some kind of group of letters. The context is pronounced as gave and brave, but in here in have it is have, right? So all sorts of contextual variations are there, which makes text to speech in English fairly hard problem. They use the 3-layer MLP to solve this problem, and to the input you give not just a single character, but a character and a little bit of its context. So how is that done? So you give, so they give a window of 7 characters at any given time. So this is 3 on one side, 3 on the other side, and 1 in the middle. So this is the whole context that is given. So they give a window of 7 characters at a time, and each character is represented by a binary vector. So they take totally 29 symbols, that is 26 characters, plus 3 punctuations, so space and comma and full stop. So you can represent any of these symbols using a 29-dimensional binary vector, right? Similar to what I've described before. So 29-dimensional binary vector for each character, that times 7, that is the dimensionality of the input. So that's how you construct the input dimension, the input vector. And hidden layer has 80 hidden neurons, and output has 26 neurons, encoding 26 different phonemes. So input is text, output is sound, which is phonemes. Then the network is output is given to a speech synthesizer. This phoneme sequence produced by the output is given to a speech synthesizer, and then it actually produces running speech. Now, why do they take 7 characters, a window of 7 characters? Why not 17? Why not 11? Why not 3? So here they found that the contextual information, the contextual influence, falls off very rapidly if you look at a window of greater than 7. So I have a central character, right? And if I look at the influence of pronunciation of this character on the neighbors through a measure called mutual information, there's not much information coming from, let us say, a character 4 steps away to this character. So usually, so the context seems to be confined to about a window of plus or minus 3 on both sides. So therefore, they use a window size of 7. So they made a child read lots of words from a pocket dictionary, and so then they encoded the sound into phonemes, right? And so input is given, the text input is given to the network, and output phonemes are used. When the trained network, the training performance increased and kind of saturated at some point, and this is similar to how human skill learning works. So when you learn a skill, right, initially you will make rapid gains, but with practice, you slowly saturate and you show this kind of a saturating curve of performance. So network also shows that kind of thing. And the hidden layer presence was quite important because when they trained the same data set, when they use same data set to train a perceptron, it was doing very badly. The highest performance didn't go beyond 82, with a perceptron, but with an MLP with a hidden layer, right? And when they use 120 hidden neurons, performance went up to 98%. And what is interesting is that the stages of learning were quite interesting and gave insight into how humans learn speech. Because one of the first things that it was found was the network was able to classify between vowels and sounds. This is what I was telling you in the last class, that the neural network will be able to extract features. It will be able to generate representations which are not meant by the training process itself. You're not explicitly trying to create those representations, they emerge by themselves. So even in the early stages of training, the network was able to classify between vowels and hidden layer responses were able to classify between vowels and consonants. Whereas in the training, we never gave that information to the network. We have never even used the concept of vowels and consonants in network training. Then the network was able to pause at word boundaries. It knows that whenever it sees a kind of a blank space, it needs to pause. There should not be any sound in the output at that time. It learned that. So in the early stages, the output of the network sounded something like a babble. That is, you say something and then the small pause, and say something else again, a pause, and so on. After about 10 epochs, that is 10 presentations of the entire data set, the speech was understandable. It was intelligible. What the network was saying could echo. And even when it was making errors, they were meaningful because it was making close calls. Instead of thesis, it would read as these, which was very similar. And it rarely confused between vowels and consonants. And some errors were actually due to errors in annotation. That is, there were bugs in the data set itself, the training set itself. And that's why it was flagging that as a wrong output from the network. But actually, network was right, but the data annotation was wrong. So performance on test set is somewhat lesser than the training performance, but still reasonable. It's not very bad. And one thing that is very important property of neural networks is what is called graceful degradation. If you damage the network uh, gradually, the degradation in the output also happens gradually or gracefully. So in this case, there is added some noise to the weights and increase the noise amplitude. And up to some level of noise, let us say about 0.3, you see that there's no difference in the output performance. The network is very robust, right, in that sense. And only beyond that 0.5, you start seeing that the performance goes down slowly. Then what they've done is they took a network which is degraded like this by noise addition, and then they trained it further. So when you train the network for the first time, this was the learning curve. Now, when they started with the damaged network, it's pre-trained but then damaged halfway. Then when you continue to train it, this time it learned much faster and reached the peak performance much faster. Okay, so that's another interesting feature. Then that is not very important from a artificial performance point of view. This network, it took longer to learn the soft C, that is C mapped onto the sound, compared to the hard C, that is C mapped onto the curve sound. And that's probably because the hard C occurs about twice as often as soft C in the data set. Okay, so that like that you can create a kind of an application like text to speech conversion very simply if you just have a good data set. But with the deep networks and CNNs and all, you can do a much better job. You can do much more powerful, more accurate, more natural sounding text to speech converters. So finally, I'll